Resistors in series and parallel configuration. Now you can see that when I have two resistors in series configuration, resistor with resistance R1 and another one with resistance R2, connected in series with a battery which applies a voltage delta V, the current that flows through the circuit is called I, and I call the current that flows through R1 I1 and R2 I2. Now, if an amount of charge Q1 exits R1, the same charge has to enter R2. So if I have a charge Q1 exiting R1, it has to flow and go to R2, so it should enter R2. Why? Because we want to avoid charge accumulation. All right? So we have the charge that leaves and enters the same, so charge is basically conserved here. So what does that mean? It implies that the current that enters R1, the charge that enters R1 per unit time, or the charge that exits R1 per unit time, is equal to the charge that enters R2 per unit time. So I1 equals I2, which is the common current I that flows through this circuit. So it's the same current that flows from this terminal and enters this terminal. Okay, what about the potential difference? If you look at the potential difference between the terminals of R1, I will call that delta V1. So I have here delta V1. And for R2, I have delta V2. So this is plus minus, as you can see here. So I have total potential difference, delta V, that must be equal to the battery potential, is delta V1, the potential difference across the terminals of R1, plus delta V2, the potential difference between the terminals of R2, must be equal to, now what is delta V1? Delta V1 is the current that flows through R1 multiplied by its resistance. That's Ohm's law. And delta V2 is the current that flows through R2 multiplied by its resistance R2. And I1 and I2 are the same. They're equal to the common current that flows through the circuit. So this is I times R1 plus R2. So the potential difference, delta V, applied by the battery must be equal to the current that flows multiplied by the equivalent resistance. So basically what I would like to do is replace these two resistors with a single equivalent resistance. All right, so this will give me an equivalent resistance of R1 plus R2. So basically what I have done here is I have connected a single resistor with resistance R equivalent. So this is R equivalent across the terminals of this battery. So this is basically connected to delta V. All right, so this has been replaced with this circuit. So what does that tell me about the series combination of resistances? The requirement that they must have the same current flowing through and the voltages should add up to the potential difference between the two terminals. I must have in series combination the equivalent resistance is sum over all the resistances, sum over I, Ri. Okay, so that's the situation for series connection. Now let's take a look at parallel connection. In parallel combination, the potential differences across the resistors are the same. So R1 and R2, they share the same potential difference, delta V, which is equal to the delta V potential applied by the battery. And the current that flows through R1 is I1, the current that flows through R2 is I2, and the total current I is basically the current supplied by the battery. So I have the requirement that the potential differences should be the same because these are metals that is connecting these two points. So delta V1, the potential difference across the terminals of battery R1, must be equal to delta V2, that of R2, and delta V, the voltage applied by the battery. But the current I will split at the junction. So you can see that this current enters the junction and it will split to I1 and I2. Now the conservation of charge at this battery, at this junction point, basically requires that the amount of charge that enters per unit time must be equal to the amount of charge that leaves the junction per unit time. So this tells me that the currents should add up. So I must have I equal to I1 plus I2. So what is I1? It is delta V1 over R1 according to Ohm's law. And what is I2? It is delta V2 over R2. And delta V1 and delta V2 are equal to delta V multiplied with 1 over R1 plus 1 over R2. Okay, now if I want to replace this combination of two resistors with an equivalent resistance here, what should be that equivalent resistance? The current that will flow through the equivalent resistance will be delta V divided by R equivalent. And this is equal to I, which is delta V times 1 over R1 plus 1 over R2. So you can see that delta V's will cancel here, and so I will be left with the following equation. 1 over R equivalent is 1 over R1 plus 1 over R2. So R2 plus R1 over R1, R2, if we write this with the common denominator here, you can see that R equivalent is basically R1, R2, the product of the resistances divided by the sum, R1 plus R2. So that's the situation for two resistors connected in parallel. But in general, we can write for many resistors connected in parallel combination, we must have 1 over R equivalent equals to sum over I 1 over Ri. So we must add the reciprocals of all the resistances to find the reciprocal of the equivalent resistance of the circuit. Okay, so once again, we are replacing the circuit here with a single circuit that has an equivalent resistance R equivalent, and it will have the same current flowing through. The current will be equal to I. in this case, we must have also the same current I that flows through the equivalent resistance. So this will be I and delta V, and that's equivalent resistance. The same situation here. All right, so what have we seen? We have talked about resistors connected in series and parallel. In series combination, the requirement of charge conservation tells us that the current that flows through the two resistors connected in series should be the same, but their potential differences should add up to the potential of the total potential difference between the two terminals. That's delta V supplied by the battery here. And this basically gives us an equation between the equivalent resistance and R1 and R2, as R equivalent is R1 plus R2. So this requirement basically leads to the addition of the individual resistances to give us the equivalent resistance in the series combination, which is going to replace this circuit with this circuit. Now, in parallel combination, the potential differences between the terminals of the resistors should be the same. So, however, the currents should add up. I1 plus I2 is equal to I. So conservation of charge, but at the same time, the fact that we must have equipotential points here, these are connected by metals, this is basically telling us that the current will split at the junction. So the total current, I1 plus I2, is delta V1 over R1 plus delta V2 over R2. So similar to what we have done here, we're taking advantage of Ohm's law. And if we write the current that flows through the equivalent circuit as delta V over R equivalent, we see that the reciprocal of the equivalent resistance is equal to reciprocal of R1 plus reciprocal of R2. And if you write this with a common denominator, it's R2 plus R1 over R1 R2, and then take the reciprocal, you see it's R1 R2 over R1 plus R2. But for more than two resistors connected in parallel, we can write reciprocal of equivalent resistance is sum over the reciprocals of the individual resistances.